All right, today we're going to unpack the fundamental operating system of the natural world. The engine that powers pretty much all life on Earth. We are talking about the ecosystem.
So let me ask you this. What could a massive forest, a tiny little puddle, and a glass aquarium possibly have in common? Now, it sounds like a riddle, right? But the answer gets right to the heart of how nature is built. See, they might be wildly different in size, but they all operate on the exact same set of rules. They're all ecosystems.
So, how do they actually work? Well, before we can see the engine run, we kind of need to look at all the parts. Let's start with a really clear definition of what an ecosystem even is.
At its core, an ecosystem is all about one thing: interaction. It's this dynamic relationship between the living things, what scientists call the biotic components, and their non-living or abiotic physical environment. And here's the kicker: neither one can exist without the other.
This slide breaks that down perfectly. Just picture a simple pond, okay? The biotic, or living stuff, that's the fish, the algae, the frogs, all that. The abiotic, or non-living parts, that's the water itself, the sunlight hitting it, the temperature, and the mud and nutrients at the bottom. The real magic of the ecosystem happens right where those two lists meet. So, every system needs an engine, right? A power source to make it all go. And for just about every ecosystem on this planet, that power source is the same: our sun, blazing 93 million miles away. But how does all that energy from way out there actually get into the system here on the ground? It all comes down to a process called primary production, and it's a beautifully simple idea. Plants take sunlight and, through photosynthesis, they turn it into chemical energy, or what we call biomass. This is the absolute bedrock of the energy budget for the entire community. It is step one for everything else that lives. And the scale of this is just, well, it's mind-boggling. Every single year, the entire biosphere, that's all the ecosystems on Earth combined, cranks out about 170 billion tons of organic matter. That's the weight of all the new plant life created in a single year. Just think about that.
But, and this is a big but, not all of that energy is up for grabs. See, plants, just like us, have to burn some energy just to stay alive. That's called respiration. The total amount they make is the gross primary productivity, or GPP. Think of it like a total paycheck. But after you subtract what they use for themselves, you're left with the net primary productivity, or NPP. And that is the take-home pay, the slice of the energy pie that's actually available for every other living thing to eat.
Okay, so we've got this stored up energy in the plants. Now what? How does it actually move through the system? Well, this brings us to one of the most famous ideas in all of biology, the great web of who eats whom. Now, the simplest way to track this flow of energy is with the food chain. It's basically a straight line that shows energy moving from one level, or one organism, to the next. And it always starts with a producer, the one that made the energy in the first place. And this is a perfect classic example. You've got the grass, that's our producer. Then the grasshopper, a primary consumer, comes along and eats the grass. The frog, a secondary consumer, eats the grasshopper. Then the snake eats the frog. And finally, the hawk swoops in and eats the snake. Each one of those steps is called a trophic level. So here's a really important question. Why don't food chains just go on forever? I mean, why aren't there 20th level consumers? The answer is a crucial rule of nature called Lindemann's 10% law. It turns out that at each step up the chain, a staggering 90% of the energy is lost, mostly just as heat from living. Only about 10% actually gets stored in the body of the organism that gets eaten. It's an incredibly inefficient system, and it's the fundamental reason why top predators are always so rare. So we've seen how energy flows in one direction, and then, poof, it basically runs out. But what about all the physical stuff? The dead leaves, the bodies, the waste. If that just piled up, the whole world would be buried. This is where nature's absolutely perfect recycling program kicks in. This critical process is called decomposition. All that dead organic matter, which has a great name, by the way, it's called detritus, is broken down by this hidden army of decomposers, like bacteria and fungi. They take complex organic molecules and return them to simple inorganic forms that the producers can use all over again. And it's not just one step, it's a whole process. First, bigger critters like earthworms break the detritus up into smaller pieces. Then, water leaches out some of the nutrients. After that, bacterial and fungal enzymes get to work chemically breaking things down even more. This creates a stable, dark stuff called humus, which finally gets mineralized back into the basic inorganic nutrients that plants need to grow. And just like that, the circle of life is complete. Okay, so we've looked at the individual parts, right? The components, the energy flow, the recycling program. But how do scientists look at the entire structure and function of an ecosystem all at once? How do they see the big picture? Well, they use this fantastic tool called an ecological pyramid. It's a really simple visual way to represent the different trophic levels in an ecosystem, with the producers, the plants, always making up the base. Now, the first type is the pyramid of numbers, and you'd think it would always be a nice, neat pyramid shape, right? Well, in a grassland, it is. You have millions of blades of grass supporting thousands of herbivores. But it can also be flipped upside down or inverted. Think about one single massive tree. That one producer can support thousands and thousands of insects, which in turn only support a few birds. So you get a tiny base with a huge level on top of it. Next up is the pyramid of biomass, which looks at the total weight of living stuff at each level. This one's usually upright too, but weirdly enough, it can be inverted in the ocean. How is that even possible? Well, you can have a pretty small mass of tiny phytoplankton supporting a much larger mass of zooplankton simply because those phytoplankton reproduce and get eaten incredibly fast. Their turnover rate is insane. But here's the most important one. The pyramid of energy is the one pyramid that can never, ever be inverted. It is always upright. Why? Because of that 10% law we just talked about. There is always less energy available at each level as you go up. This pyramid is the perfect visual for that one-way, rapidly shrinking flow of energy. So we get how these systems work, but what are they actually worth, to us humans? In dollars and cents? Well, some researchers actually tried to put a price tag on all the services that healthy ecosystems provide for free. The number they came up with is almost hard to believe. 33 trillion US dollars per year. That's nearly double the entire global economy at the time. And where does that staggering value come from? The answer might really surprise you. A full 50% of it comes from just one service, the formation of healthy soil. Just think about that. The rest is made up of things we often just take for granted, like nutrient cycling, climate regulation, and of course, providing habitats for wildlife. And that really brings us to our final and maybe most important question. These systems that power our entire world, from the tiniest puddle to the biggest ocean, are providing us with services of almost unimaginable value, and they're doing it all for free. So, knowing that, how might we start to rethink nature's real value in our own daily lives?